Hello, everyone, and welcome to another session of Control. Today, we continue with a new chapter, system analysis. In the past, we talked about system modeling. We found the relationship between and input of the system and the transfer function. We found the transfer function, what is output in terms of input. Now, we want to find output itself, not in terms of input. What is the curve of output? How the output looks like? And we analyze that. We discuss the variation and the value of output, the final value of output, if it depends on the input or not. So we discuss this kind of subjects today. We have first order system, second order system. As usual, first we talk about the theory, concepts, and step-by-step solution for a given problem. Then next week or the week after, we go to this problem solving and discuss the solving some problems, questions about this subject. Okay, let me share with you the slides. I have two slides, one for first order system and one for this second order system. Is okay, clear now? Okay. Yeah, first order and then second order. So we will discuss about the first input. What is the type of input, pulse, step, ramp, or sinusoidals, and then response in time domain. That is the output of system. And we have a small theorem, very simple, to find the final value of a system. As we know from the previous sessions, the transfer function is defined by the ratio of output to the input. So output equals input times transfer function. So we know input, we know transfer function. Now we can multiply them with each other to find the output. So what is input? There are three types of inputs to study. First one is impulse. Impulse is a pulse that is very, very narrow, very high value. So it's like this. It started from rectangular, but it gets very narrower and has a very high, theoretically infinite level. Very high level. It's happened to a very, very short time. It's like a switch on and off. If you switch on just on and off in a very short time, it gives you a very shock, very high level signal or pulse. Of course, it's not used in practice, but we studied this to see what's happened. This is for understanding the system's behavior, to see that how the system is robust to a shock. You know, sometimes, for example, electricity network is getting off, shut down. Then rapid change maybe make some damage to the system. So we should know that if the system is robust to that unwanted, unnecessary, bad input or signal, so that is just for checking, testing, verification. It is not used for control. So we studied this one, and then we study this by Laplace transform. The way that we find the output is through the Laplace transform, because Laplace transform simplify the system by multiplication of transfer function with the input gives output. But if you want to go to not Laplace transform, time domain, it is very complicated. We'll see that how complicated it is if we go through the time domain. So Laplace domain is very easy to analyze. So what is the value of this? What is the Laplace transform of the this impulse input? And when we find this, then we just multiply with the output. We can find the value of output. So here you see the Laplace transform for this impulse input is just simply A. just a. So constant number, very easy. So in time domain, it's a delta, this delta, which is a very, like arrow, uh, shape, peak, very peaky poles. But in Laplace transform, it is proved that the Laplace transform of this function is a constant number, just area of a. Then step. Step is the most commonly used because it is like switch and keeps on forever. When you turn on the switch, then you let it on and keep it open forever. Okay, that is step. Step input. The time domain is like a, the amplitude, a level, and in Laplace domain it will be a over s. All of these equation, this transformation will be given to you. If we need this in the solution, the exam, I will give you all of these equations, no worries. So yeah, in this special case, when there is just a constant number of 1, then we say that this is unit step function. The third one is ramp. Ramp is just a steep going up, steadily going up. But this is not useful because it goes to infinity in theory. So we don't use it, but for a shorter time we can use it. For a limited time we can use it. It's AT. So for example, at time t, the voltage is 1 volt, time 2, 2 volt, 3 volt, and so on so forth. So it goes up. So and then Laplace transform is given by a divided by s square. So if a is called 1, then we call it unit ramp or speed function. So just review of these three: a over s, a over s2 for impulse, step input, and ramp input. Okay, now everything is ready to find output. We have input in Laplace domain, we have system models in transfer function format, then the output will be input times the output. So yes, here for the first type step, we have a over s, g of s. G of s is given, is a system model, or you should find it before. And then the time response is just to find the inverse Fourier transform or inverse Laplace transform. So inverse Laplace transform is very mathematical. It's very computational. I don't go through this calculation. I will give you the result of the transform function in time domain. I'll give you a table of this if you need. So you will find the output in terms of Laplace domain. Then after conversion, using the table or the formula given to you, you will find simply the output. Okay, let's talk about the first type. Assume that we have first order system. First order system means that we have just a capacitor from our inductor, just one element of saving energy. So then the result will be a first power order here, tau s. You see, gamma over 1 plus tau s. This is the transfer function for the first order system. So I multiply this with the input to find the output. Transfer function times the input gives the output. Okay, so this is in Laplace domain. So in Laplace domain, we have some table, LT, Laplace transform table, and we look at the table and we'll find that transfer function, that inverse time domain transfer function for that transfer function, and then you will see the time domain as output. Okay, so here there are some mathematical calculation here to find out for those students are interested in mathematics to find out how to find the inverse Laplace transform. Here are the way that we can do it by splitting the fractions, but these are not required to present in the solution in the exam or anywhere. This is the way that we can find this directly without using the lookup table. Okay, so yeah, here we have residue, fractional split technique, and we find these the roots of the denominators, and then we find that residual, and we find this. This is mathematical, but as I mentioned, no need this step by step. So for mathematics, engineering mathematics, you had it before in engineering mathematics. Now we just use the results and discuss the results, how the result is, and what is the behavior of system for this result. So you'll see the result is a over small a times 1 minus exponential of minus a t. So it is an exponential function. A is input, the amplitude of input, and a, this is small a, which represents something that we say that this is the behavior of system, the dynamic of system, is time constant of system. So represents the time constant. So what is time constant? Yeah, there are some concepts that I want to introduce it now. So this is the general solution for the first order system. As you see, there are two components, two parameters. A, which is about input, capital A, and small a is about the system itself. So A is small a, is inverse of tau. Tau is time constant. What is time constant? Time constant is a new concept that, very new concept, that the time duration that takes the output to achieve 32%, 63.2%, around 63% of the input. So if you look at the curve, yes, here, you see this is the curve of output. This is the result of output. So this time, from 0 to 63.2% of the final value is the duration of time constant. So any system, first order system, has a time constant value, which means that how how quick works systems, how fast it is. So it's about the speed, about the reaction of the system, response time of system to the input. If the system is very fast, then tau is very small, very small. For example, here tau is 1, for example, 1 second. Then we have 95% time. There is no name for this. Just to see that after 95%, after 3 seconds, we will arrive at 95% of output. And then after about 5 seconds or minutes, we can reach at the final value. Still not exactly final value, but it's very close. Okay, so you learn the step. You need a step with the time constant. So 63.2% of the final value is called time constant. Okay, so now impulse. What is output of impulse? So for unit step, we saw this. So this is the response for the unit step. What about unit impulse? So impulse means you give the input in a very short time and then turn it off. So it is only happen in a very short time, everything. So again, by doing some calculation, we come up with this output, gamma over tau exponential of minus t over tau. So the output looks like this. You see, the first time going up, it started from up, and then since the switch gets off, then it comes down. The output also comes down, follow the input. So you see again that it is like attenuative response, and after again five unit of time, it comes down to the ground, to the 0 point, lowest value. So here are some practical, some partial fraction expansion to find out the output in time domain. So it is the mathematical way of finding the output using inverse Laplace transform for RAM. How to solve this mathematics, as I mentioned, is not part of this module. This is just for your information. And for the RAM, okay, so for step, unit step, finish, impulse, finish, now ramp. Ramp means that we give this this input, the speed function, steady goes up, and we'll see the result is like this. Follow the input, but with a drift, with a time shift of tau. At most, yes, almost tau for that. Oh, okay. So you see that it's good, but for a given time, for a given limited time, not always, because we don't want to have a very high output. We should be on control. So within a limited time, it is okay. And finally, for this part of lecture, for first order system, we have a final value theorem. Final value theorem is not limited to first order. For any system, for any linear system, we can apply this final value theorem. Final value theorem is the theorem that gives us the final value of the output without any calculation in time domain. So you don't need to find the curve of output and then look at the final value and see how much is the value. No, you don't need that calculation. Just apply this simple theorem in Laplace domain, and we'll find that very easily. So the theorem is given to you, no need to memorize this, which means that the limit, the value at infinity is given by this. Let's see, someone maybe needs to permit accept this one, and then I will back. Okay, sorry for that. Final value theorem is about the value in infinity, the final value of the system, output system. So for example, very easy, it says that the limit of function in time domain at infinity equal the limit of function at 0 in the plus domain. So in time domain, the limit in infinity equals to the limit in the plus domain at 0 when s approaches to 0, of course with multiplication of s. So it means that when we find output f of s, which is already found before, final the output value f of s, we found it before because we know system modeling, the transfer function, we know the input, so we multiply these two, and then that one is the output in the plus domain. Very easy, like this one. For example, g of s is given to you, or you will find it, the transfer function. This is given to you in the question, that is input. So you multiply these two, this input and this gives you f of s, that is the output. So multiply these two, and then multiply the result with s. S is fixed. S is not for this question. S is for the theorem, which is in general fixed. So S times that multiplication result gives you the final value. Very easy. You don't need to find the time domain equations and put t to infinity. It's very difficult in that way. So very easy to apply this to find the output. You see here that if you put S0 here, 0, of course, not defined, but there is S, remaining S. So you should multiply this X of S with S. So there is S here, okay? That S will be canceled by this S in the denominator. So we have one S, constant S always. That constant S is cancelled out with all times the S that is coming from the input. So then you substitute S with 0. So 0. So 15 divided by 0 plus 3 will be 5. A very simple example. So in the exam, we have such a question, a very easy question in one part of the system analysis question. Okay, so today, as I mentioned, we have two parts, step first order and the second order. So first order finish. Now I move to second order system. See that what's going on with second order system in the output. So in the first order we saw if unit we have such a curve like this. If we have impulse, it comes down like this. If we have ramp, it goes linearly parallel with input. That is for first order system. Now we go for second order system. Second order system means the power of S is 2, not 1. So it will be a little complicated. So, but we focus only on step, only this one, not ramp, not impulse. Okay, so just we focus on, so this will be impulse. Okay, just we focus on step input only. Okay, and then we will see what is happen in the output. So here we have some new concept, because the output of the system is not that smooth going up. It has some oscillation. We say damping. We have some like vibration, some oscillations with some frequency. So we have natural frequency or undamped natural frequency. When it is under damping, we have some frequency of damping. How much the system is oscillated, how fast, by omega n. It's determined by omega n. So now the standard form of the system model, we have two things: system model, that is transfer function, and input. Input is clear. Input is only here we consider step, that is 1 over S. So input is 1 over S. So transfer function is this one. So this equation is a standard and will be given to you in the exam. Omega n squared over S2 plus 2 zeta omega n S plus omega n squared. So zeta is damping ratio, the rate of damping. Omega n is the natural frequency or undamped. So if you say natural frequency, it's okay. Simply natural frequency. Because frequency is happen when we have damping. If we don't have damping or over damping, there is no any frequency or oscillations. Okay, so here these equations are the way that we find that output. So we try to find the output
عندنا شويه شغل داخل
we want to find the output equation by mathematical calculation. So again, these are not part of this
يعني هيثم اخبارك اقول لك هيثم
module.
ضغط
It's
الفيديو بيتنا
about
عشان تساعدنا شويه عندنا شغل
mathematics
خبر بعد
in
عمك في فتره هنا
mathematics.
تعال على زين عندنا شويه شغل
So
داخل
it has
هيثم عمك عمك
complicated form to find that equations.
يعني هيثم اخبارك اقول
We
لك
have
هيثم ضغط
of
الفيديو
course
بيتنا
some
عشان تساعدنا شويه
table
عندنا
for
شغل خبر بعد
this,
عمك في فتره هنا
but the
تعال
result,
تفطر
we
عنا
look at
زين
the result only. That's
عندنا
that
شويه شغل داخل
equation.
بعدها
So
عندنا مع
I
اولاد
can
عمك
give you this in the exam. I don't need to memorize it. So you see that we have not only exponential. In the first order, we had only exponential. If you remember from the last
يعني
slide,
هيثم اخبارك
we had exponential of something. Exponential means that goes up or come down smoothly. But if we multiply it with cosine, some sinusoidal signals, cosinusoidal signals, it has some damping. So it will be like this. So the output will be one of these curve. Depends on that value, how much damping we have. Under damping, no damping, or in between. So there are three regions that we can distinguish. Under damping means it is on damping.
تعال افطر عندنا لا
Damping.
تنسى
So zeta is less than 1.
اقول لك هيثم
So
ضغط
if zeta
اليوم
is
بيتنا
less
عشان
than 1,
تساعدنا شويه عندنا شغل
we are
يعني هيثم
above
اخبارك
that
اقول لك هيثم
level.
ضغط اليوم بيتنا عشان
All
تساعدنا
these
شويه عندنا
curves
شغل
that are
خبر بعد
above
عمك
this,
تجي فتره هناك
above this final value, because final value is the value that we gave to the system, like 1. So we gave 1 volt in the input and we see the behavior in the output. But if the system acts like oscillatory response, then we have this above this. So we have initially some oscillations. But if zeta is greater than 1, so who says zeta is greater than 1 or less than? The system itself, the transfer function of the system. So you know this is the transfer function. See again. This is the transfer function. Yeah, this one transfer function. So this zeta, this number here, you look at this number. This number is greater than 1, then your output looks like this. Yeah, this one. Yeah, over that. We say cannot overshoot. Here we have overshoot, but here it is undershoot. So it is below that final value. So in between, in the border, we have a critical damping, exactly zeta 1. If we have only just one value, and just that one value, zeta equal 1, we have a very fast response. See, the response is very fast. So very fast going up. This is very slow, it takes time to reach the final value, but it's very fast. Of course, the faster of this will be the other one. So this is one criteria that we can apply for designing controller, how fast the control should be. If the control needs to be very fast, then zeta should be a small number. You see here that, see, this is very fast, goes up very fast, but it has some overshoot, something over the value of input, which is not good. So if you want to have very smooth but slow system response, then you have to choose a very large zeta, large number greater than 1. So it depends on the demand. You choose zeta for transfer function to have this, your desired response. So you see the envelope of this, the push of this curves is like the exponential, because the function we have is exponential. Exponential means some function is smoothly here and as an envelope. So this multiply with the sinusoidals, so it has 2 components. One component that is about attenuation of these peaks, and one component is inside, which is oscillation of the curve. So these are mostly for your assignment. In the assignment, we have a question about this, and you will find this curve not by manual drawing, by MATLAB. Small part of the question is about MATLAB, and you need to implement this formula in MATLAB in Simulink. We will teach you how to do it by lab sessions after Ramadan. We have lab session maybe 1 or 2 weeks after holidays. We have lab session for MATLAB learning, and in that session you will learn how to plot this curve for first order and for the second order system. It's very easy. So you see the typical curve this for second order system is like this. So now we have more discussion. It's about system analysis. So how we can analyze the system. So until now we learned that if zeta is less than 1, it is like this. If it is greater than 1, it will be like this. If it is 1, it is in between. But we have more characteristics, more parameters, definitions for this kind of system. For the first order system, it was very easy. We had only one parameter, one quantity, which was time response, or response time constant. Just one. The time that achieved to 63.2%, 63% of the final value, we call it that time constant and finish. We didn't have any time. But here we have more time. Rise time, peak time, settling time, periodic time. So different times with different formula. For each of these, we have formula, and all of the formula, of course, will be given to you in the exam final page formula sheet. So just define it how and what they are defined, how they are defined. So rise time is the time that takes from 10% to 90%. So how much time takes for output to reach from 10% to 90% of the peak, the final value. So that is the definition of rise time. So we have formula for that. Peak time. Peak time is specific time. It's the time happened output. Peak. The maximum value of output happened at peak time. Peak overshoot is this is not about time. It's about the value of overshoot. How much peak overshoot? How much is that value? How much overshoot? So very easy to see that the value of output at peak point minus the value of output in the end, or steady state. SS means steady state value, or the final value. This length, this height, this difference from output to this constant value is called a peak overshoot. Settling time. Settling time, TS, is the time that the system is settled within 95% of that. You see here, the system first goes up very, very high, but then goes down, and then again up, and then approach to the final value. So how much takes to be very settled, very close to final value? 95%. When it reaches 95% of the final value, we call that point of time settling time. Okay, time for response to reach and remain in a specific ratio within 5% in this case, or 95% of final value. So 5% means very close to this, to that final value. 95% means that here, from the 0 point ground to that level. So how much takes to reach that point is called settling time. We have formula for that, and number of oscillations, how much oscillations we have, how many of these peaks we have. So again, we have formula also for this. For rise time, the formula is given. Formula, actually, we will see this formula. formula. Omega d, so omega d is, we call it damped ratio. I will give you the formula for that shortly. Tangent, pi minus tangent, the square root of 1 minus square, zeta square over zeta. And then zeta. Zeta is some numbers that controls the rate of oscillations in the output. So it is a typical time, as I mentioned, if it is very high, it is very small, a very slow system. It will be overdamped, so it's not good. But if it's very small, then it goes very high overshoot, which is not good. So some values between 0.4 and 0.8 is preferred. So this is some value for your assignment to design the controller. Time to peak or peak time is given by this formula, pi over omega d. And peak overshoot is given by this formula, that is the value of the output in the peak maximum condition. And we have percentage of maximum value to the final value. How much overshoot we have in terms of percentage? We have this formula. And for the settling time, the formula is this. So settling time, as I mentioned, is 5%, 3 over zeta over omega n. So this is fixed. 3 is fixed for 5%. If I say 2% or 10%, then that 3 will be different. So we have a question about this in the revision. In the final exam, I will explain how to work with different percentage and how to find settling time for different percentage of output. Number of oscillations before settling time, those peaks and valleys is given by this settling time over periodic time. So settling time, we have formula, we can obtain that. Periodic time, we have formula for that time. So then division of these two gives us the number of oscillations. So this is a curve for some numbers in terms of zeta, different numbers. So zeta, 0.2, 0.3, you see? Then we come from small numbers to large number, we come down. So the smallest zeta, the larger the output. And of course, with more oscillations. So I give you an example. So omega d, I didn't define that. This is given also to you in the exam and formula sheet. Omega d is damped. Damped, when we have damped situation, we have a frequency omega n square root of 1 minus zeta square. So we saw omega d in different formula. You see here, omega d. Here is omega n, okay? But here you see omega d. Yeah, this is omega d, here omega n, okay? So here we need omega d, for Tp, for Ts, Tr also omega d. So this omega d is given by that formula here, omega n square root of 1 minus zeta 2. Yes, this example for RLC system, like the system that I solved last week. I found the transfer function like this one, something like this, depends on R and LC. I found it in general. So now we want to find the output. How is the output for this system? So first, we'll find the transfer function. This is transfer function. Then we multiply with input. And then omega d. So here, you don't need to do this calculation in time domain like this. I give you this formula. You know, from here, let's go back to the formula. Yes, this one. Yeah, this is the formula for output. We have another formula, general. Yes, this one. The output is this. So you don't need to calculate or obtain this. I will give you this. This is the general format formula for output of second order system. So what you need to put here, omega n, omega d, and zeta. So your job is to find zeta, omega n, and omega d. So then you put in this formula for the output. So no matter how the system, under damped, critical, any types, any conditions, no matter, you will find the numbers, this omega and omega d and zeta, and find that. So now if I give you this example with the RLC value, so you will find at time omega n and omega d here. Yes, omega n, we will find omega n. This is omega, if you remember from the standard equation, 2 zeta omega n and omega n. This is omega n squared. Omega n squared is 4, so omega n will be square root of 4. And then 2 zeta omega n will be 2, and then you can find zeta. So next class, I will explain it in handwriting. So I give you example to find this, and I will solve that example. So just want to show you the step by step. You should find omega n, zeta, and omega d. That's it. So if you have these three, then they can put these numbers in that equation here. Without this, this is the way that we go through the Laplace transform and inverse Laplace transform. And here, full solution will be this. The final solution, based on that formula, will be this omega n, omega d, and zeta. You put this, and it will be like that. And if you ask you what is periodic time, what is rise time, or peak time, you can find them very easily, because you already found omega d. You have formula 2 pi omega d. You have formula for rise time, tr equals this, and everything is given, and just replace these parameters with those numbers that you found before. And peak time also, the 2 pi over omega d, and we'll find that one. This is like example of final exam question. Yes, everything will be there, and then C of TP. What is that? Is C peak, the value of peak point or overshoot point is given by that formula. I gave this formula to you before. So just put those omega d, omega n, and TP, because TP you found it before, right? Yes, this is TP, and we will find that value for the peak value. And also in terms of percentage, so the difference between peak value and final value divided by final value gives you the percentage increase, or just overshoot percentage. You see these results. And for settling times, 3 over zeta omega n, everything was obtained before, just replace them here. And then number of oscillations, settling time divided by periodic time is number of oscillations. It is 0.8. It means that we have around 1 oscillation, which means that not fully 1 oscillation, just less than 1. I think that I have a curve. Yes, here you see number of oscillations is not 2, is not half, little between 1 and half. Yeah, in half and 1. So the other time also is shown in the picture. You see the plot. 1.2 here is the rise time. Yes, here. TP 1 point is here is 1.814. That is the peak point. And TS settling time, you see that happen at T equal 3. And periodic time 3.6. And peak overshoot is 0.2092 or 16%. So you see this value of overshoot, 16%. Okay, that's it for system analysis, second order system. I will give you one or two examples with solutions another time. Of course, next week we have holiday, and the week after we go to campus. So then I will solve such questions about second order system with handwriting on board. So the next subject after that problem solving session, we have a new chapter for complicated systems. If we have more than first order and second order systems, with a fourth order, higher order, what we do with that? We have some simplification procedures about the block diagrams and some rules to simplify this, and that is the subject for the next. This is the rule of simplification. Just prepare your mind for that level. I will discuss this after that problem solving session. Okay, that's it for today. As you see in this final concluding slide, we talked about the rise time, peak time, and settling time, and a step response to second order systems. And we defined the natural frequency and natural and undamped natural frequency and damping ratio. Okay, so simplifying the block diagrams is the next chapter. I will cover it after problem solving this session. Okay, that's it for this session today, class. If you have any question, let me know. I hope that everything is clear. Clear? All right, thank you so much for your attention. And yeah, happy Eid.
Okay, thank you, teacher. Thank you for your explanation.
Thank you. See you.
And Eid Mubarak.
Eid Mubarak to you all.
Inshallah.
Inshallah.
Thank you.
Thank you. Thank you. See you in 2 weeks, inshallah. After 2 weeks, I will see you, inshallah.
Inshallah.
Inshallah. And have a nice time and goodbye.
Nice time. Goodbye.
Thank you. Thank you. Thank you.